Today, I will talk about the mega drought prediction in North America to share with you. So this is first, this is motivation of this research. So this is a historical record of U.S. Mega drought evaluated by trailing records based on the overpeak, Woodhouse and overpeak in 1998. So color indicate the major mega droughts, and then we can see the couple mega droughts in the past 300 years. So in particular, like the 1930s, it's a very huge drought, and which is called as the Dust Bowl. So during the Dust Bowl, soil is completely dry, and continental wind is very strong. As a result, dust storms like this follow are observed in many regions. So this kind of drought is affect to the agricultural loss, and they may cause to the economic loss. So from here, so we just have a very simple scientific question. Can we predict the mega drought event like this event? So in terms of the time scales, mega drought will be related to the low frequency decadal climate variability. So if we can predict this kind of drought, it will be very useful and very beneficial for society. However, it is quite hard because precipitation has a very short memory. So this figure shows the predictability of precipitation based on the ECA model according to 2002. So it's a perfect model. So it's a kind of potential predictability. So when we can see the upper panel, this is the first year lead time of predictive skills. So color indicates the anomaly correlation coefficient. So that color indicates higher predictive skills. And then we may find some skill in the North America or some other region. So first year may be okay. But when we see the decadal time scale, like a lower panel from 1 to 5 years lead time, there are no predictive skills. So based on this result, mega drought prediction will be hopeless, no meaning, or ridiculous or something. So you may think it's nothing, very nonsense. But here we want to think about what is a drought. So this is a hydrological process in NCAR model, NCAR random model, CRM4. So precipitation is one of the very good measurements for drought, of course. But drought is also related to the soil water condition. So in the CRM4, soil water has two layers, soil layer here and the aquifer water. So some of the water in these two layers is called as a total water storage. So in today's talk, I will show the total water storage is potentially predictable on decadal time scales, even though there are no predictive skill of precipitation. So this is a model experiment. We use a couple model low resolution version of CESM 1.0.3. This is quite low resolution. Atmosphere and the land model has a T31 horizontal resolution, and the ocean and the sea ice is a 3 degree curvature grid. So based on this model, we conducted the 1,000-year-long fully industrial control simulation, and then first 100 years the spin-up period. So I just analyzed the remaining 900 years. And based on this control run, we conducted a hindcast experiment for 2,000 years. So pick up the initial condition from control run, and we adding a random perturbation in the atmosphere, and we make a 10 ensemble members, and then conduct a 10-year-long hindcast prediction every 5 years. And total, we have 39 initial cases in this one. So I will show the result of analysis for the control run first. So to identify the dominant mode in the North Pacific hydrological North American hydrological variability, we just conduct EOF analysis for annual mean precipitation in the upper panel and total water storage anomaly in the lower panel. So when we see the pattern, it's quite similar. So positive in the north and negative in the south, indicating the meridional seesaw. But when we see the principal component, it is completely different. So precipitation has a very high frequency component, and it looks like a kind of random. So when we see the power spectrum, it is almost white noise. But when we see the total water storage, it has a quite low frequency. And when we see the spectrum, it is a quite redness. It's quite slow. But anyway, important thing is that total water storage has a very low frequency. So from this result, we can expect total water storage will be long-term predictive skills. But anyway, it's in this point, we may confuse because the correlation is looks very low. So in the next slide, I will explain what is the relationship between annual mean precipitation variability and total water storage based on the water budget equation. So this is the water budget equation. W is the total water storage, and P is the precipitation, E is the evapotranspiration, which is some of the evaporation from the surface and transpiration from the vegetation. And R is the total runoff. It is some of the surface runoff and subsurface runoff, and S is the snowmelt. So based on the Deros and Manabe 1988, evapotranspiration is proportional to the, we can assume evapotranspiration is proportional to the total water storage. And we can also assume total runoff is also proportional to the total water storage. So as a result, these two terms is represented like this damping term. And in the snowmelt is negligible in this case because we use the annual mean, and then it will be very small. And precipitation will be like a kind of white noise as I showed before, so we just put on here. So this equation is completely same as the AR1 processes. So in the AR1 process, next year our total water storage is represented like this equation. And the epsilon is a white noise, and here in this case it's related to precipitation. So we just expand this equation like this way, and then as a result, total water storage in the next year is represented by a current precipitation, or 1 year before precipitation with weight, and 2 years before and weight, or something like that. So from this equation, we can easily imagine soil layer act as an integrate of precipitation, and it's kind of filter. So based on this concept, we try to explain the relationship between annual precipitation and total water storage. So this is the same figure as I showed before. And then this is a AR1 processes. So from this equation, we estimate alpha from this time series, which is just autocorrelation with 1 year lag. And precipitation is quite white noise. So we put on this time series in this here, and then reconstruct the total water storage variability from based on this simple equation. So, and then black line shows this reconstructed water storage variability. It's very highly correlated. So from this result, we can see the precipitation is quite random, but its low frequency component is very important to induce water storage variability. And because soil water is acting like a low-pass filtering effect. Of course, we can also confirm the same result based on the running mean filter for precipitation. So this is a 10 years running mean filter for precipitation anomaly, and then it shows the first EOF mode. Of course, we apply the low-pass filter, so precipitation, path spectrum shows the red noise, but pattern is quite similar in those cases, and temporal variability is highly correlated with total water storage. So we can easily imagine that precipitation is a white noise, and it's kind of input, but output shows a red noise. And this process is completely same to make a coffee. So it's a kind of rocky filter. So when we pour the hot water from the top with high frequency or something, but it doesn't matter because output of coffee is quite low frequency. And this low frequency part will be highly predictable in terms of the theoretical case. So, so this is the main result. And then as for next, so this kind of precipitation variability is highly related to the atmospheric downstream jet activities. So this is a relationship between precipitation anomaly in the first EOF mode correlated with the upper level or lower level zonal wind. So contour is the climatology, and color is the correlation. So as we can see, that there are tripole pattern in the west coast of North America, and it is a biotropic structure because we can see the same stuff in the upper and lower level. And this is located to the downstream jet. So this means the downstream jet activity like a narrowing or widening. This kind of activity induces precipitation variability over the North America. Of course, we can see the same result when we apply the relationship between zonal wind and total water storage in the first year more. So the pattern is quite similar. Of course, there are some differences in the upper level, upstream jet activity, but in terms of the downstream jet activity, this kind of jet narrowing or widening is very important to induce land precipitation variability. And it induces a low frequency component of total water storage, and it would be, theoretically speaking, total water storage would be predictable on the long time scale. So to confirm, so from here, we just simple question, because it's just only theoretical approach. So if question is, we can really predict the total water variation on decadal time scale or not. So to confirm these questions, I conducted a hindcast experiment based on the perfect model. So model is perfect, and there are no model biases in here. And then based on the EOF pattern, I just pick up the area average in the northern part of America and southern part of North America. And so and this is a time series of total water storage anomalies. So black line is a control line, and from this, and then we assume that this is kind of real world or real observational data. We just assume. And then based on this control line, we put in a random perturbation in the atmosphere, and they conducted a 10-year-long hindcast experiment, like this blue, red or blue colors. So every 5 years. So I just only plot the line alternatively. So as we can see for this hindcast, hindcast very quite follows the observed, model simulated total water storage variability. So, and the right panel shows anomaly correlation coefficient. In other words, these are predictive skills. X-axis indicates the predictable year. It's measured by, which is obtained by how many years predict anomaly correlation coefficients beyond some criteria. And vertical axis indicates the precipitation, and soil water average from surface to each different levels, and the bottom is the total water storage. So when we see the red line, like a precipitation here, there are no predictive scale, of course. But the soil becomes deepening, predictive scale becomes long. And in this case, total water storage have almost 5-year predictive skills. So when we see the same stuff in the southern part of North America, we can also see the consistent result. And in this case, southern part, precipitation have a 1-year-long predictive scale, but soil becomes deepening, predictive scale becomes long. And in this case, total water storage have almost 10 years long predictive skills. This kind of predictability is also confirmed by maps. So this is an anomaly correlation scale map of total water storage in the first year lead time in the upper panel, and 2 to 5 years lead time in the middle panel, and 6 to 9 years lead time in the bottom panel. So in the northern part of North America and the southern part of South America shows a very long predictive skills. So from this result, we just see the soil water is a very highly predictable on decadal time scales. And probably this soil water variability will be also affected to the vegetation variability or wildfire frequency variability. So we just check what kind of scale can we find in vegetation, carbon, and wildfire occurrence. So this middle panel, center panel is a vegetation carbon, and the right panel is a fire frequency. So of course, vegetation carbon is very long predictive scale because vegetation change is quite slow. So it is predictable maybe. But fire, when we see the fire frequency, some regions still have a very long predictive skills. For example, in this grid point, it is quite long predictive skills. So in the next slide, I will show what kind of relationship can we see between among total water storage and vegetation carbon and the fire frequency in some grid point. So I just pick up this point, it's just V. everything is very high predictive skill. And another grid point is just marked S. Also, in this grid point, total water storage and vegetation has a long predictive skill, but so fire frequency is not so predictive. So first, I just show the V grid point of V. So in this grid point, vegetation is a very dominant role. So this is a time series of wildfire occurrence anomaly in the line, and color in the upper panel is the soil water, and color in the bottom panel is the vegetation. And so line is completely same. So when we see the relationship between fire and soil water variability, its correlation is quite small, almost no correlations. But when we see the fire and vegetation time series, it's quite frequently. So like this event, vegetation is going up, and then after that, wildfire occurrence is also enhanced, and it induces a mortality of vegetation, and it's going down the vegetation curve. And then fire frequency is also reduced. So it's kind of cycle. And this is a log correlation, so like this one. So indicated it's a cycle between vegetation and wildfire occurrence. So in this grid point, vegetation and fire interaction is quite dominant, and it may affect this soil water. But when we see the different grid point, situations also different. So this is a different grid point, and when we see this one, during the dry condition, fire frequency is quite enhanced, but during the wet season, like blue line, fire risk is very reduced. And the correlation between fire and vegetation looks quite small. So in this grid point, soil water is a major driver for fire frequency and vegetation variability. So soil control the fire and vegetation. And then soil water also may control the vegetation in terms of the correlation. So this is summary of my today's talk. So as I say, downward westerly jet activity in this precipitation variability in North America, and this is kind of white noise. And then this is acting like a driver for soil water variability, and this soil water variability is also related, have an interaction with the fire frequency and vegetation variability, and maybe it's also related to the carbon nutrient cycle or something. And in terms of the predictability, precipitation is a very low predictive skill, but soil acting like a low-pass filter, and then soil water and fire and vegetation, this kind of stuff may have a decadal predictive skills. So this is a perfect model result. And if you want to see more detail, it's published in Climate Dynamics, so please check this one. If I have much more time, how many times? One. Yeah, so it's funny, I just want to discuss what kind of ocean impact induce a downward stream jet activity. I didn't show this result. And then it does a couple of climate phenomena to affect this variability probably. But probably main factor is a tropical Pacific forcing. So like an ENSO or ENSO flavor, this kind of stuff will be in this downward stream jet activity. But unfortunately, these two guys have a very low predictive skill in terms of decadal prediction. So this is a predictive skill measured by Japanese model, MIROC. So blue one is a hindcast experiment, so it's initialized in the ocean. And black is persistence, and this is the ENSO scale. So ENSO scale is usually it's less than 1 year lead time or something. So this is a month, so it's 1 year. So it's kind of 1 year something. And some people may think that ENSO flavor, like a El Nino Modoki, it has a decadal variability. So it may have a very long predictive skill. But unfortunately, skill of ENSO Modoki is much worse than the ENSO. But it is like this blue line. But the funny thing is that if we extend much more longer lead time, it's kind of phase recovery of this stuff. So it's kind of very funny, very strange behavior. So recently we found a new climate mode. We say the tropical transversing variability, and it may be one of the hope to induce a decadal variability in North Pacific hydrological variations. So in the trans-basin variability, we just say interaction between Pacific and Atlantic. For example, like a late 1990s, Atlantic SST is warming up, and it induces upward motion in the troposphere, and it also induces downward motion in the tropical Pacific, like Walker circulation changes. And this downward motion is also related to the cooling in La Nina-like pattern in the Pacific. So this kind of modulation, Pacific-Atlantic seesaw have a very low frequency variability. It's a decadal time scale. This is a pattern of sea level pressure associated with the trans-basin variability. We pick up this region, and then take a difference and measure how long this mode shows the predictive skills. And when we see the blue line, it's quite long, almost 3 years or in advance or something. So when we see only tropical Pacific, spatial scale is very small. So predictive scale is very short. But when we see the entire tropical Pacific, it is a large scale compared to the El Nino. And then time scale is much longer, and then predictive scale is much longer. And there probably will be also some impact to the downward jet stream activity in North America. So this will be one of the possibilities to induce a long predictive scale over the North America. That's it. Thank you.
Okay.
So I have a number of questions and issues with what you've done. We've done a lot of work with soil moisture and looked at the e-folding time scale of memory. Memory isn't more than about 3 months, and so I don't understand how you can get annual memory in soil moisture unless you include the deep aquifer, which has no influence on climate. So even if there's a slow memory in the deep, you didn't explain what soil moisture model you used and what its memory is, and whether it agrees with observations. But even if the deep aquifer has changes slowly, why is that important for decadal prediction?
Yeah, and in this model, aquifer water is also water exchange between the lower level soil water and aquifer water. So it does an exchange. So aquifer water changes also affected the soil water in the bottom layer. It's a CLM random model, a CLM4 NCAR model.
Have you checked it against observations to see whether it really moves the water up and down at the right speed?
It's a good question because it's a perfect model, so it's only modeling well. So
it was based on BATS originally, and BATS, this Dickinson model, originally had a much too slow exchange with the deep water, and so there was memory in the model that wasn't there in the real world. So I think until you validate the model with timescales from observations, I have questions about whether there's really that memory there.
Recently satellite observation GRACE, they measure the total water content, and then it shows that some kind of decade or trend, but it's very short.
But GRACE doesn't even have data for decades.
True, exactly. So it's very short. So it just only shows a trend or something. But in our result of our result, it may be part of the decadal probability. It's a possibility.
But GRACE doesn't separate the water and the soil.
It doesn't separate
the atmosphere and the deep water.
And they didn't separate, But deep water is much water content.
So when you compared the time scale of the prediction scale, there was one plot comparing the. That's no better than the Markov model, which is persistence.
Yeah, it's persistent, exactly.
So you basically they're saying that the water, whatever the quantity you're predicting, is just persisting. And the time scale of predictability is just the persistence.
Yeah, so first, in terms of first order, persistence is a quite big rule for the long-term predictive skills.
Visualized prediction is no better than the persistence.
Yeah, but so problem is that we only have about 10 ensemble members, and then so this black line is a Markov model with 1,000 sampling. It's a quite huge amount, and it's completely persistence. Of course, it is much worse than the persistence in a hydrogas with 10 ensemble member. But when we see the different region, it sometimes extends.
This is the deep water volume doesn't affect the atmosphere. Because that's affected by soil.
Exactly, it doesn't affect the atmosphere. But it's probably important for the water resources. And then because this theory explained by only forcing from the atmosphere. But probably low frequency part of atmosphere may be contributed from the low frequency ocean variability. And then this kind of process would be filtered out about the high frequency precipitation variability in the atmosphere. The possibility.
Yeah, I was a bit puzzled by your initial spin-up. You said the coupled system reaches some kind of equilibrium in 100 years. And when we run the coupled systems, it tastes like we ignore the first 500 years because everything is changing so much.
Yeah, true.
And what was your metric to say that this thing equilibrates in 100 years?
It's based on the surface temperature balance or radiation balance. So in terms of the radiation balance, first 100 years is good enough. But of course, it may be not so good and we need to see much more later part, but probably will be consistent, I hope.
And then for the last part, you said you found a new mode of climate variability.
Yep.
And then you titled this memory. Where is the memory coming from?
It's many memories. One is maybe AMOC variability, and then it may induce a tropical SSC variability.
So why is it new then? If it is related to AMOC and if there's a tide, then there's always that tide.
Yeah, important idea is it's an interaction between Pacific and Atlantic. So once Atlantic is changing, and then Pacific is also responsive, because previously Pacific is active rule. We think Pacific is active rule to induce the global climate variability. But in terms of the decadal time scales, Atlantic is also some rule to induce a Pacific variability. So it's an interaction.
Is this a model result or observation?
It's a real hindcast, so observation is also same stuff.
One more question.
I just wanted to ask you about your coffee filter model. Doesn't the soil moisture also influence precipitation? Isn't there a feedback rather than just one direction? I think the fundamental question about drought is how much is local feedback. It's not so much your memory, but it's feedback with the atmosphere, and how much is externally forced by advection from, say, SST patterns.
Yeah. So in this case, precipitation is almost, so total water storage is almost responsible to precipitation variability. So it's a whole thing, and it's kind of response. And then
I'm thinking on much shorter timescales than the annual.
yeah, in the much shorter time scale, it may be some feedback, but I didn't check it. So because it's only focused on the decadal time scale. So, but it will be interesting questions.